We'll talk a little bit about calibration and validation. We sort of jumped ahead in the presentation this morning over this topic. So before lunch, we had finished setting up our WMOST model. We optimized. We looked at the results. Vicki, next slide, please. So we had defined our problem. We went to this item in purple, did a WMOST scenario setup. We optimized. We looked at the results. Vicki discussed some of the other scenarios you may want to run and sort of repeat the process to look at the sensitivity of the results to the assumptions and the input data. We skipped over an important topic, which is calibration and validation of the WMOST setup. And next slide, please. So what do we mean by calibration? So calibration is the step that you go through to verify that what you've represented in WMOST is a reasonable representation of the real world. So the water balance that you're calculating matches what you would get if you were to look at stream flows in that same watershed. So the way that's done is you set it up for known conditions. So this would be for a portion of the flow record, and when we say a portion, it's basically a number of days or a year in the flow record. You represent all of the model characteristics for that same period. So your demand is going to be for the period that you're trying to calibrate against. Same with other operations. You don't allow management actions to be used during the optimization. So you still click on optimization when you run the model, but there's no action that's being allowed to be selected because we want WMOST to be forced to basically deal with the system as we've specified it. You would not, similarly, you wouldn't set target stream flows because we're not trying to really accomplish a goal, we're just trying to calculate the water balance. And you look at the results, see what we have, and adjust inputs and parameters as needed to try to improve the fit if you're not happy with the results. And we'll go into a little bit more discussion as to why would you need to do that. The validation part, you'd basically be doing a very similar exercise with a different time period. You also have measured flow, say, for a second year. Run through the setup, don't make any adjustment in any of the parameters, and see if basically the good fit that you had achieved during calibration is retained. You're still satisfied with it. And the flow may represent different precept. You want to make sure that whatever relationships different are built into the model are preserved.
Yep. I have a
question?
So you said measured flow record. Now, isn't the runoff and recession value that you get from HSPF or spot model, isn't that already calibrated value?
Yes,
and
it will have been
calibrated again.
So yeah, that's a good question. What we have for our basin are representative HRU responses for that basin. Our land use characteristics may be slightly different. We may have more or less. So it's per acre. And when we specify the number of acres that we have, we get sort of a net calculated runoff and a net calculated recharge. We want to make sure that whatever flow comes out of that setup matches measured flows that you would get from a gauge. So that's part of the reason why we want to do that. So how do we do this? The first step, there were 6 steps in setting up WMOST. The 5th one was the flood module, which we saw was not a mandatory step. Similarly, the step 6 is to input measured flow. It's not mandatory to run a simulation model, but it is needed to calibrate and verify that the model produces results that are reasonable. So in step 6, the last item on the list is measured stream flow. You click on that that button, it opens up a tab, similar to all the tabs that we've seen this morning, where it lets you copy and paste a time series of flow data. And the time series, could come from the USGS gauge. It could be a time series from a simulated model where you have basically estimated simulated flows at the location that you're interested in. It can also be other data sources, and we've included some examples in the source document on the CD. One example could be the safe yield estimator for Massachusetts, where it's basically based on regression analysis. So that could be another example for an unstream gauge. There are other data. So you would import your measured flow, optimize again, and I'll repeat, you basically turn off all the management options. At this point, optimization is more of a water balance calculation. So you calculate your water balance. The model, WMOST, allows you to view a graph that will basically overlay as a time series your measured data that's showed in blue in here with your showed in WMOST calculated flows. That's in black. And you access this diagram or this plot by going back to the input tab and simply clicking on that button that says compare to measure flow. And this will basically overlay the two. So you're looking at this and you say, well, so what do I make of it? When you're evaluating whether your fit is good, you need to consider what are you trying to manage, and that will give you maybe a different perspective on what you're looking for. So if you're trying to develop management actions that will address low flows, you'd be paying particularly close attention to your time series to see if the low flows are represented reasonably well. So that will give you a set of management actions that would be better from that perspective. High flows, similarly, if you're looking at flooding, you'd want to make sure that your peaks are sort of close, and average flows if it's sort of different perspective. There are basically two main evaluation methods. One is a visual evaluation and looking at patterns of fit, and by that we mean are the magnitude reasonably close, is the timing also acceptable, and then there are statistics that modelers use to evaluate the goodness of fit, where that sort of comparison is presented as a metric. So we've included some of the common statistics for goodness of fit. The flood peak, lower flows, flow variabilities, and there's more information about that in the documentation. And then the example case studies are provided for WMOST. What WMOST provides right now in version 2.1 is the ability to look at the fit visually. So the default interface doesn't calculate the flow statistics yet. That's something that can be built in the next version. So let's look at what you might be able to do. You look at the graph and you are at the time series, and you notice, for example, that your estimated flows are higher than the measured flows, and you seem to overstate on a number of days. So there's a few things you can adjust in our experience. One that the model is sensitive to is the groundwater recession coefficient that's found in the groundwater tab. And that groundwater recession coefficient basically is the relationship between groundwater and surface water. it influences sort of how flashy the response is to the precipitation, so the runoff and the recharge. You can also, because you might have transferred information from the bigger watershed, in our case study example, it was the Sudbury watershed, you've transferred baseline and runoff from that location, applied it in a different location. It may reflect precip data that's not representative of your location if the weather station is located far away. So another place where adjustments may be made to the input data is the baseline runoff and recharge. And one way to do this is to apply a multiplier. So at 5%, you expect that your runoff is actually 5% higher than what comes out of the model by default when you use this baseline hydrology module. You would take your runoff time series offline, multiply by 1.05, paste them back in. So that's the way you would do that. And we've used these two methods sort of on some of our applications in WMOST, and that typically sort of does the trick.
Could you just start off, instead of using model output like it is PF or SWOT output, which is not going to have 100% goodness of fit. There will be some issues with the model output. Could you just use gaze data, if you have gaze site, like you just use the total street flow, partition it to the runoff and base flow coefficient using just base flow calculator, and use that as an input? As an input
for your runoff and your recharge?
Yeah. And then that will reduce uncertainty associated with what you've received gotten from the model as well. Because this model, like you're bringing a PF output, which is already uncertain. Right. If a daily Daniel Moriarty says that greater than 50.50 MCA is good, but you should have more than just 0.50. Right, or it could have been calibrated in a part of the watershed that's far away. And then you probably do not have good match between recharge or base flow and runoff. So, I mean, what I would do is I would just take the stream flow from USGS station and partition that into runoff and base flow using base flow calculator, which is available. You can use digital recursive filter. Now, there are many ways to partition runoff and base flow, and then use that instead of using model output.
But you need land use. Partition it by land use.
Right, you need land use.
Partition it land use.
Yeah, so there's, you can use a coefficient. You'll have to use coefficient for each land use, the reduction coefficient.
Yeah, so by then, basically, the decision is whether that's going to give you a more accurate picture than using a model that, even though may not be perfect, has been calibrated, hopefully, well. So we can go through an example of this actually using the Westboro model, where we ran it and we artificially ignored the groundwater retention coefficient that came out of the model and said, okay, let's just change that value and see what we get. So if we do that, Vicki, next slide. This is the time series that we get when we muck with the groundwater recession coefficient that we obtained from the model. And the three circled areas that would be of some concern. In particular, that third circle of the more horizontal oval is for the summer months, and those are the months for which we had targets. So you really want to be closer to the measured flow during that period. That's the period for your management targets. But we're also sort of below our measured flows at the start of the period in January, and we seem to be not as flashy as the natural response for that interim period in the spring. So when we change the groundwater coefficient, groundwater recession coefficient, focusing again on the three circled areas, we don't see a degradation overall of the fit in other areas, but we've greatly improved the fit for those, for the start of the period, for that spring period, and in particular for the summer period where we're really focusing our management action. And this calibrated model uses a groundwater recession coefficient of actually slightly higher than what came out by default from the baseline, but not very far. So the baseline automated setup would give us a groundwater recession coefficient of 0.07, and we bumped it up slightly to 0.08, and that gave us sort of best performance. So it's a little bit off, but not very.
Use the peak flow rather than low flow.
Right.
If you're including groundwater recession.
So that is the way we.
Can I just make one comment? So this, what we get out of the HSPF model and we import it, if we compare that to the HSPF stream flow, we get a great match without any adjustments. Here what we're showing, and this just for helpful background, we're showing the model stream flow based on HSPF data, but we're showing quote-unquote measured stream flow that comes out of the SYE, and the SYE is, I would say, a rougher estimate of stream flow, and there are a lot of even negative stream flows in there that are then later zeroed out in the methodology. So that is partly why some of the fits you see here, at least those who are modelers among us, might say, oh, there's some rougher spots. And the SYE tends to be flashier in terms of you see a super high peak flow, but then you also see almost zero flows. Because it's simply a regression equation. It's not a water balance model. So as I mentioned, it does have negative stream flows that are zeroed out, and similarly, so it'd be hard to get a model to actually represent and replicate that flow.
Thanks, Vicki. Any questions on this calibration example? So there are a couple of issues that may occur as you do this. When you optimize, you could have, because you're basically modeling a constrained system that doesn't have management options being turned on and available. It's entirely possible that your system cannot meet the demand, the historic demand, using the historic actions or the historic supply in the system, some amount of water. You would see that by I don't even know what it is, gazillion dollars is the closest I can get. That basically indicates there's no feasible solution. What we recommend in that case, and it could be as just there's one day in the whole simulation that your water demand and your water balance is not met, and that's all it takes over, say you have a 5-year period. So we've built in this last ditch option. That's the surface water, the makeup surface water option that I covered earlier this morning in the infrastructure tab, and that basically lets it go pick this amount of water to make up the water balance, and it at least allows you to see some results and see what's going on and what day or days are causing the problem. It could also be that you're running out of groundwater. Your groundwater recession coefficient may lead to a response that's too fleshy. You may have insufficient groundwater in your system at the start of the simulation or during the simulation. So these are sort of suggestions on how to resolve the issue to get basically a working run to play with and make further adjustments.
So if you were to turn on makeup surface water option, then you would also get the values there, right?
Yes, you would basically,
the penalty.
The penalty would show up in the third. That's a good point. You would see that penalty in the third row. And then your total annual cost would reflect the fact that that penalty was selected. Any question on validation?
We have one question here.
I don't understand what makeup water penalty represents. Could you say that again?
Were you able to hear that
Yes.
question? Okay, great.
So the question was, can you please clarify what makeup water penalty is? Is that the question?
Yes, correct.
So the makeup water penalty will reflect the fact that the system, that WMOST needed to go basically create water and apply to the amount of water. It's going to calculate a volume that was insufficient in the system, and it will use that volume as sort of a virtual reservoir. But it will also calculate the cost associated with this amount of water. And in the infrastructure tab, we had specified for this option a cost per MGD, and we had specified a very cost when we go through our menu of options. We want this option to be selected as a last resort. So when it goes through the simulation, it finds out that, oh, I'm missing 1,000 gallons to balance my system. It will take that 1,000 gallons, it will apply to it the cost that's been specified in the infrastructure tab, and it will show you in the results the product of that 1,000 gallon times the cost as a penalty. And that basically indicates that somewhere in your system you're running out of water. Does that answer the question?
I think we're all set here.